Are you going to say hello?
John, you can say hello.
Okay, fine. You don't want to say hello?
Hello.
All right.
Right, John took it down to say hello. Just sticky note, put it underneath.
I thought we were all going to say hello.
Okay, let's we're going to talk about reading F to F prime to F double prime graphs first, and then we'll do linear motion, so one directional motion, that's velocity, acceleration, speed. So we'll talk about that at the end, but for now we're going to talk about going from the original to the first derivative, from the first derivative to the original, and all that good stuff, okay? All right, so let's say we have this graph, which is of f of x, and it tells you a few things. It tells you that the slope at 0.5, this slope is 1, and then it tells you that the slope of 4 at 4 is, the derivative is 1/3, so the slope is 1/3 at 4, right? Okay, so if we graphed on the derivative, if we graphed the derivative graph of this, then at 0.5, my derivative is 1. So we put a point at 1 for the derivative. And then at 4, my derivative is, my slope is 1/3, so I go for 1/3. On this side of 0.5, is the slope greater or less than 1 on this side? There's a greater, right? So for all of the values on this side, the derivatives will be greater, and they get like steeper and steeper on this side until it's almost undefined slope, right? And then as you go from 1 to 1/3, the slope of your tangent lines are getting like, shallower, right? So the slopes are getting smaller. So your derivatives are decreasing. I don't think it ever actually levels out, but it gets super close. So your derivative graph actually looks like this. Okay. Why is the derivative always positive? Eric.
Because it's square root function, so it can never be negative.
Yeah, so this graph is always increasing, which means that your slopes are always positive, so your f primes will always be positive. Fly is in my hair. Okay, get it? All right, now let's go to example 2. Oh my gosh. It's on the paper.
Where's dissection?
Oh. Okay, so here. I got it.
Oh!
RKO out of you. You're going to bury it?
It's gonna move. It's gonna like fly.
It's gonna fly again.
You didn't recycle the sticky note.
No, I didn't.
Are you trying to destroy the
Okay, ready? All right, now that that distraction is done with. Okay, right here, so down here it just says like, hey, look at the left and the right. We're just gonna talk about it here. So if you look from left to right, from here to here, what is the graph doing? What is f of x doing? Okay, increasing here, and then also from like here to here, you are increasing on the f of x graph, right? So if f of x is increasing, then you could say that the slope is positive, which means f prime of x should be above the x-axis. Yeah, positive. So from 4 to infinity and from negative infinity to 4, your first derivative is positive if your original is increasing. You see? Okay, from negative 1 to 4, your graph is decreasing. It's decreasing. So your slope is negative, which means your first derivative should be negative or below the x-axis, right? So negative. Okay. All good? Right here, we hit where the slope of the tangent line is 0, right here and right here. So if the slope of your tangent line is 0, then your first derivative should be 0, right there and right there. Okay. When your original changes from increasing to decreasing, you hit a max, right? So that's when your derivative changes from positive to 0 to negative. This is like positive to negative, right? Positive to negative means you're going to hit a max. And then right here, you're at a minimum, and your first derivative should go from negative, if you read from left to right, to positive, right? And that will tell you that you have a minimum on the original graph. So maximum on the original graph, the first derivative goes from positive to negative. Minimum on the original graph, first derivative goes from negative to positive. Everybody okay with that? Yeah? Okay, right here where you hit a minimum at like 2 down here, this point right here. If I go back to my original and I put a point at like 2, what does that look like on the original graph? Yeah, come on. Almost. It's a little bit above though. Point of inflection. Thanks, Keon. So this is a point of inflection. Do you remember point of inflection from Algebra 2 and pre-calc, right? And point of inflection means that your original is changing from like from here to here. You are concave what? Down, right? And then from here up to infinity, you're concave up. Okay. So if your original is concave down, and then you have a point of inflection and then concave up, what that means is that your first derivative will go from decreasing to increasing. So if your first derivative goes from decreasing to increasing, then you know your original goes from concave down to concave up, and you have a point of inflection right in the middle. All right, so you can get a whole bunch of information from any one of these two graphs, and you should be able to go back and forth between graphing the two of them. Do you know the definition of concave down and the definition of concave up? So concave down graphs, if you draw a tangent line on any part of a concave down portion of the function, the tangent line's going to lay on top of the curve. Okay, so any tangent line that I draw, the function will be below the tangent line. and any part of a concave up graph, a tangent line's gonna be underneath the actual curve. Okay, so if you draw a tangent line at any one of these points, the tangent line's gonna be underneath the actual curve. All right? Excellent. Let's do this one now. Give it a try. Try graphing the derivative, knowing the original, and go with increasing, decreasing, where you think the point of inflection is, maximum, minimum. You don't have to follow that A, B, and C step, but
Maximum on 3 or 8?
you can go with 3 point something. I don't think you can't.
So just
Yeah, just do a. The shape should look the same, and the intercepts should look the same, but you really can't say how high it's gonna go. Unless you approximate the slope, like right there. If you want to. Sure, that's how high you should go. Positive 2/3, right? Okay, shall we? So, I like to look at this graph and I like to say, oh, here at -2, my slope of my tangent line is 0, and at around 3, maybe 3.1, the slope of my tangent line is 0. So if I do like a graph, here's G, and then here's at -2 and at, let's say, like 3, to make it easy. G prime is what? 0 and 0, right? Okay, right here on this side, G is decreasing. Yeah, you're close. I haven't gotten there. So G prime is negative. Exactly. And then right here in between, G is increasing, which means G prime is positive. And then G is decreasing, which means G prime will be negative. Okay, so I should hit 0 at -2 and at 3. Anywhere you have a maximum and minimum. Okay, and then this is a minimum, so I've got to go from negative to positive. So I'm going from negative to positive, and then I'm going to negative again on this side. Right here, where did you say your point of inflection was?
0.7.
Let's go with 0.7. All right, so at 0.7, then you should hit a maximum on your first derivative. So you're increasing, so you're positive. So this would be your graph of your G prime. Okay? Good? Better? Cool. All right. Now, there's a relationship that you've got to know. So, if I tell you that f of x is increasing or decreasing, that means that you know that the derivative is positive or negative. So if the original is decreasing, then you know that the first derivative is negative, right? If the original is increasing, then you know the first derivative is positive, right? Okay, if the original is concave up or concave down, then you know whether the first derivative is increasing or decreasing, and then you know whether the second derivative is positive or negative, okay? So I can tell you any one of the parts and you can tell me what everything else is doing. Okay. So here's our example. If I give you that the first derivative is decreasing, tell me what f is doing and tell me what f double prime is doing. What is f doing?
Down.
Concave down. And what is f double prime? Negative. Okay, do you see the relationship? So if you want to prove any parts, if you want to prove concave down, you can either prove that the first derivative is decreasing, or you can prove that the second derivative is negative. But you should know this relationship, and that will help a lot when you're determining the values of the first and second derivative. Okay, here's f prime of x. I want you to go backwards and work and see if you can find out what the graph of f of x is. Okay, so this time you're going, this is the derivative. Try to go back to the original. Okay, it doesn't matter how high or how low your maximums and minimums are, but you should have like a maximum here, a minimum here, a maximum here, and a minimum here. And then you should be hitting points of inflection halfway in between. I didn't do such a good job on those, but they're okay.
Do it like that on a test or was it perfect?
Yeah, it would be good. It'd be fine. Actually, on a test, if like later in the year, they're gonna give you like additional information that lets you connect it a little bit better. But for now, like I'm just looking for maxes and mins in the same x value that your your derivatives zeros are.
Should we draw like reference points?
No, you don't have to. I can see it. Okay, all good. All right, so on delta math, a lot of it is like just looking at f and f prime and comparing the two. So that will be your first half. The second half is linear one-directional motion. So a lot of times it's going to give you a position function, and most of the times they'll use a particle, so that because particles can like move anywhere, but sometimes they'll give you specific examples, like a thing moving horizontally would be like a car or a person. But we only have like one directional movement, just like back and forth. And then vertical is usually in terms of S of t is your normal like position function. Horizontal is x of t, saying like, hey, this is x. I don't know why they use s for vertical. But this is like a rocket that like goes straight up in the air or comes back down, or like a ball that goes straight up and then comes back down. But either one, this is always position. So this will always give you like things in terms of meters, feet. I don't know any other units that we use. Yards, whatever. Okay, so we have average rate of change, which can find our average like velocity, or now we have instantaneous rate of change, which can find us instantaneous velocity. So if what's the difference between velocity and speed, by the way? Yeah.
Speed's an absolute value.
Right. Speed has no direction. Speed is just like a number, a positive number. And velocity is the speed plus the direction. So if velocity is greater than 0 on a horizontal line movement, that means that you're moving right. Yeah, you can say forward, but like just think of it as right. Most of the time they'll say right or left. And then v is less than 0, you're moving left or going back. And if v equals 0, you're stopped. And a vertical line, if your v is greater than 0, if your velocity is greater than 0, you're moving up. Yeah. V is less than 0, you're moving down. And if v equals 0, you're also stopped. Yeah, you're probably changing directions. But sometimes you stop and then you go in the same direction. So if you're changing directions, then you have to switch from positive to negative or negative to positive. Right. And then Matt just said speed is the absolute value of velocity, so it has no direction to it. You just find velocity and then do the absolute value of it. And then when you find the rate of change of velocity, that's called acceleration. So it tells you how quickly something speeds up or slows down, how fast the velocity is changing with respect to time. Okay. For motion, on a horizontal line, if acceleration is greater than 0, you can kind of think of it as you're being pushed to the right. So even though you're being pushed to the right, you still could be moving left. Do you know what I mean? Like somebody can push you, but you could still be like going forward, even though like you're like fighting against them. If your acceleration is negative, then you're being pushed left. And if your acceleration is 0, be careful. That doesn't mean that you're not moving. It means that you're like, velocity is constant. So it's like you're on like cruise control in your car. Do you guys use cruise control anymore?
Yeah.
Yeah.
Yeah, gives your ankles a break. Using cruise control. The scary thing is like, have you ever pressed the up button, the plus button, or the like minus button? I'm like, how much is it increasing my speed by? Yeah, it scares me. Vertical line, you're being pushed up, and if your acceleration is negative, you're being pushed down. Same thing for equal to 0.
Yeah. I see it.
I don't think it works that fast though. Oh gosh. Okay, let's talk about speeding up and slowing down though, because speeding up and slowing down doesn't just mean like, hey, is your velocity positive or is your velocity negative, or is your acceleration positive or if your acceleration is negative. It's the both of them combined. So if you're speeding up, that means that you're moving, let's say you're moving with a positive velocity. If you're speeding up, that means that your acceleration is also pushing you forward in that same direction. So if you're speeding up, then your velocity and your acceleration are going to have the same signs because they're working in conjunction with each other and they're pushing you forward a lot faster. If they're working against you, if your velocity is positive but your acceleration is negative, that means that you're moving forward but you're being pushed backwards. That means that you're slowing down. You're not moving as fast. Does that make sense to you guys? Okay. And then negative velocity, you could be moving backwards but somebody's pushing you forward. Yeah.
That means you could be slowing up and speeding down.
What? Slowing up? I mean, I guess.
Going up, but you're slowing down.
Oh, I see what you're saying. Yeah, I guess so. If you're talking about vertical movement. Oh my gosh, John. Stop it. Haha, you're hilarious. Okay, what I want you to do this is giving you the velocity graph. So you'll know a lot of things about position. Don't worry about position too much anymore. But you'll know a lot of things about velocity and a lot of things about acceleration from this graph, right? Because you should know if velocity is increasing, that means your acceleration is positive, right? Okay, so I want you to skip a couple questions on these because I haven't talked about area under the curve yet. So go up through 12, just draw a little squiggly line and then stop there. Actually, skip 11 too. Save that for later. And then start back at 21 and do from 21 to 28. Okay, so skip this little section. The last 4 down here and the top 4 up here. Skip those. Okay. Chat and work together on this. You can move around if you want to talk to people that you want to talk to. And then try the last 2 example problems on the next page where I actually give you the functions. It should be pretty simple, those 2 parts. Okay? Move around, chat, hang out, and discuss.
Physics helps so much.
All right.